Continue with section 1.3 on the curvature of connections. So, as a way of introducing where curvature comes from, I just want to remind you about commuting of partial derivatives of real functions. So let's suppose x is a manifold and f going from x into the reals is a smooth function. And let's also suppose that x upper 1 up to x upper n are local coordinates, local smooth coordinates on some open set in X, though mostly our local really means on some open set for me, local coordinates on X. So then, well, the second partial derivatives d2f dxi dxj is equal to the second partial derivative d2f by dxj dxi. So in other words, so partial derivatives d by dxi and d by dxj commute. As you know, provided f has enough smoothness, if it has two continuous derivatives, let's say, but I'm always working with smooth functions. Okay, now in differential geometry it's kind of bad style to choose coordinates when you don't need to. So instead, or alternatively, in coordinate free notation, if, let's say, v and w are vector fields on x, then, well, we can write it in terms of the derivative in direction v of the derivative in direction w of f minus the derivative in direction w of the derivative in direction v of f. Well, so you might think that would be 0, but actually it's not. There's an extra term. It's the derivative in direction brackets v comma w of f, where this here is the Lie bracket of v and w. So one basic operation is if you have two vector fields v and w, can form a third vector field brackets v comma w, which involves the derivatives of both v and w. And you can kind of check this just by using the formulae for v and w here. So what's really going on here is that, well, this derivative here, it involves derivatives of the second derivative of f, but it also involves the first derivatives of f and the derivatives of w in the direction v. And this thing again involves derivatives of v in the direction w. And so this term on the right it's kind of encoding the bits of this which are first derivatives in f and first derivatives of v and w in directions w and v. So then we can take, if you like, v is partial by dxi and w is partial by dxj, because the coordinate derivatives are actually examples of vector fields, and then the Lie bracket of d by dxi and d by dxj is 0. So then in that case this formula reduces to that formula because this right hand side becomes 0 if v is d by dxi w is d by dxj. Okay, so perhaps we'll also say where curly L v of f is v dotted with df is the derivative of f in the direction v. Okay. Right. So now let's suppose that E over x is a vector bundle, and nabla is some connection on E, and S is a section of E. Smooth section. Okay, so we can ask if this picture here still works. Whether partial derivatives of S using nabla. So nabla is not natural. Nabla is the connection is a choice we have to make for our vector bundle. We can ask whether partial derivatives of S use nabla commute or not. So that is, well, do we have, well, so the analogue of this thing here would be nabla in the direction d by dxi of nabla in the direction d by dxj of S equals nabla in direction d by dxj of nabla in direction d by dxi of S for local coordinates like that, or alternatively we could say nabla in direction v of nabla in direction w of S minus nabla in direction w in direction nabla in direction v of S minus what equals nabla square brackets v comma w of S. And perhaps we'll give these equations numbers, star 1, star 2. So this is what it would mean for the partial derivatives to commute for connections as well as for functions. And the answer is that no, these aren't true in general. So in general, star 1 and star 2 are false. They're actually true if and only if the connection is what's called flat. And the curvature is some geometric quantity, curvature of nabla, which is R of nabla, or just R. This is a section of, well, I shall write it as end of E tensor lambda 2 of t star of x. So end of E is just E tensored with E star. But I'm thinking about this as the bundle of endomorphisms of E of linear maps from E to itself. So we're going to define an element of this sections of this big vector bundle. So this measures whether partial derivatives using So all partial derivatives will commute if and only if r is equal to 0. And it's so there is a unique such r of nabla such that r of nabla dotted with brackets S tensor V tensor W is equal to nabla V brackets nabla W of S minus nabla of W brackets nabla V of S minus nabla of V bracket of V and W of S. And this has to be true for all vector fields V and W and sections S in gamma of E. Okay, so the right-hand side here is a section of the vector bundle E. So we're starting with a section S of E. We differentiate in direction W, then we differentiate in direction V. Everything here is in E. So here, well, this lies in end of E tensor lambda 2 of T star of X. That's in E, that's in, these are both in T of X. If you like, you can swap, you can anti-symmetrize them. You can write V tensor W minus W tensor V. Doesn't make much difference. So this dot here means that you you contract the lambda 2 T star of X with the Tx tensor Tx using the dual pairings. So those just reduce to functions. And then here you we basically apply the end of E to the E. Well, that's kind of E tensor and E star. So you kind of you contract together that factor of E containing the S part with the E star here to give you another E. So then this dot here contracts all that lot together to give you a section of E, which can then be equal to the section of E on the right-hand side. Okay, so it's a horrible formula. What's important is that the right-hand side involves, well, the 0th and the 1st and the 2nd derivatives of S. Because we're taking S, we're differentiating it once, twice here, once, twice there, only once there. Whereas the left-hand side involves only the 0th derivatives of S. Okay, so the right-hand side is kind of special in that a lot of it is cancelled out. So the second derivative, so in these, the second derivative parts of S come only in these two things, and this anti-symmetrization of the V and W has had the effect of cancelling out the second derivative parts of S. Okay, so if you only had the first two terms, then you would have been left with some first derivative parts of S, but then this third term here cancels out all of the first derivatives in S. So the right-hand side has managed to cancel out, you know, if you've been writing this in coordinates, you'd expect to have something of the form, you know, A times the first derivatives of S, well, A times second derivatives plus B times the first derivatives plus C times the 0th derivatives, where A and B and C have some kind of generalized matrices of functions. So all of the first and second derivatives on the right hand side is cancelled out. What's left is only a zeroth derivative term, a pointwise linear term, and that's what the curvature does. Okay, so if you'd written down some random expression here, then it wouldn't have worked, because you would still have been left with some derivative terms which are not accounted for on the left hand side. Okay, so well, in index notation, I'd write R is R alpha beta KL, where the alpha and the beta are E indices. Well, so the beta is really an E star, because it's lower. So the somehow upstairs indices represent E or Tx, downstairs indices represent E star or T star of x, and the K and the L are T star of x indices, because they're lower, and because it's a 2 form, it's an end of E value 2 form, because of this exterior thing here, that means that R alpha beta KL is minus R alpha beta LK. Meaning if you swap round 2 indices downstairs, these 2 indices, then you change the sign. And that's obviously true on the right hand side. If you swap over V and W, then these 2 terms swap over with the minus sign, and you change the sign of the bracket vector field there. Okay. And then we can rewrite this equation in index notation as R alpha beta KL S beta VK WL is equal to VK nabla K brackets W to the L nabla L S to the alpha minus W to the L nabla L brackets VK nabla K S to the alpha minus brackets V comma W, let's give this a different index, M nabla M S to the alpha. And actually you can do some cancellations here. No, we won't do it, sorry. Okay, right. Right, so the connection nabla is called flat if R is 0 everywhere. So then nabla is flat if and only if locally on X, meaning that you can cover X by sufficiently small open sets in which the following is true. Locally on X, there exist trivializations E is isomorphic to X cross R to the K. Sorry, this in general won't be true globally on the whole of X, but what I mean is that you can choose covers of X by open sets U such that E restricted to U is isomorphic as a vector bundle with U cross R to the K for some U open set in X, which identify nabla with partial differentiation curly D, that's just partial differential of maps x into r to the k. Okay, so if you have a trivialization of your vector bundle, if you've identified E with x cross r to the k, you can identify sections of E with smooth maps from x into r to the k, and then you can take ordinary partial derivatives of those, ordinary differentiation, just using the usual d functions. Okay, so this is a non-trivial theorem. It follows from, I think, the Frobenius theorem. So it's actually, so one direction is easy. If you can trivialize it, and then because partial derivatives commute, you'll see that the curvature is 0. The converse, that if the curvature is 0, then the thing is locally trivial. That's a non-trivial fact from kind of fact about PDEs, really. Okay. So in coordinates, if gamma, alpha, beta, k are Christoffel symbols, for nabla. So that is, if we choose some open set, and on that open set we choose coordinates on the base x, and then we choose a basis of sections e1 up to ek for the vector bundle on that open set, and then we get these gamma alpha betas representing the connection in coordinates. Then we find that our alpha, beta, j, k is equal to partial j, meaning d by dxj, of gamma alpha beta k minus partial k of gamma alpha beta j plus, well, let's write this as the sum over gamma of big gamma alpha, small gamma j, big gamma upper j, beta k, minus big gamma alpha, little gamma k, big gamma. Okay, so it involves, it's linear in the first partial derivatives of big gamma, and then it's quadratic in the zeroth derivatives. Okay, so that's what we need to know about curvature for the moment. Next section, 1.4, on connections on tangent bundle Tx and torsion. So far I've been talking about connections on a general vector bundle E. Now I want to take my vector bundle E to be the particular vector bundle Tx, the tangent bundle. So let's take X to be a manifold. So that Tx over X is a vector bundle. And let nabla be a connection on Tx. Well, there is then a natural tensor T, which in tensor index notation is the form T upper A lower BC. So it's got one tangent bundle index, two cotangent bundle indices. This is in sections of Tx tensored with lambda 2 of T star of X. So it's antisymmetric in the lower two indices. TABC is TA minus TABC. So such that well, let's write it as T upper A, B, C, VB, WC is equal to nabla VW A minus nabla WV A minus V comma W A. So here I'm going to start using the Einstein summation convention for index notation of tensors. So this means that if you repeat an index, once lower, once upper, then you sum over that index over all i's 1 up to n, and being the dimension of x. This has to be true for all vector fields v and w on x. Okay, so this is the derivative of w in direction v. That's the derivative of v in direction w. This is the Lie bracket of the vector fields v and w. So this is a bit like this equation here, except it's simpler, because this equation for curvature has two derivatives. The equation for torsion has only one. And the reason why this makes sense only for connections on the tangent bundle, not for connections on the general vector bundle, is that here I'm taking v and w to be both sections of the tangent bundle. If we had a general vector bundle, then v would be a section of the tangent bundle, w would be a section of the general vector bundle, but it wouldn't make sense to swap them around because they'd be things of different kind. Okay, so torsion is kind of simpler invariant than curvature because curvature involves two derivatives, torsion involves only one. And we call nabla torsion free if the torsion T is 0. And then for torsion free connections we have that nabla V of W minus nabla W of V is the Lie bracket V comma W for all vector fields V and W on X. Okay, so if in local coordinates x upper 1 all the way to x upper n on x, we have that the derivative of the vector field d by dxi, this is a section of the tangent bundle, is equal to sum over all j and k is 1 up to n of gamma I j k, these are Christoffel symbols, times partial by dx j tensored with dx k. If that's true for Christoffel symbols, gamma I j k, then T I j k is equal to gamma I j k minus gamma I k j. So I said before that the Christoffel symbols are not tensors, in that if you change coordinates from one coordinate system to another, then the Christoffel symbols change by not just a linear transformation law, but a linear plus constant transformation law. However, if you do this anti-symmetrization in the lower two indices, then the left-hand side is a tensor, because under the change of coordinates law for these things, this has a linear transformation law where it just transforms according to the Jacobian of the change of coordinate matrix. So if nabla is torsion free, then gamma ijk is gamma ikj. It's symmetric in the bottom two indices. Okay, well, so torsion is similar to curvature, but it's simpler because, well, T involves only one derivative, and in fact no derivatives of the gamma ijk, but the curvature R involves two derivatives and only one derivative of the Christoffel symbols gamma ijk. And our view is that torsion-free connections, that is, connections whose torsion is 0, are the best kind. So if you have to choose a connection on the tangent bundle, it's best to choose a torsion-free one if you can. Okay. Sorry?
You pull down the...
Oh, sorry, yeah. Okay, well, so now it turns out that if nabla is a torsion-free connection, on the tangent bundle of X, then its curvature R, which you can write as a tensor in index notation as R, I, J, K, L. So one upstairs indices, three downstairs indices. That satisfies two identities. Well, so the first Bianchi identity R I J K L plus R I K L J plus R I L J K is equal to 0. So here I've taken these things, I've done a cyclic permutation of the three downstairs indices. So JKL, KLJ, LJK is 0. It's also true that, or for any curvature, it's anti-symmetric in the last two. So Rij KL is minus Rij LK. If you swap around these two indices, then you change the sign. So if you like, you could also add on the 3 more terms where you swapped these 2 round. So all the permutations of these with the negative sign, and you still get essentially the same identity. That's first Bianchi identity. And the second Bianchi identity which now is going to involve the derivative of R using the connection nabla. So nabla K R I J L M. So in this formula, the first 2 indices, the I and the J, are going to stay where they are. We're going to cyclically permute over the 3 indices, this derivative here, and the last 2. So this plus nabla L R upper I J M and K plus nabla M of R upper I and J K L is equal to 0. Okay, so this is in index notation. So if nabla was not torsion free, then you'd have analogues of these equations which would also involve extra terms involving the torsion and its first and second derivatives, I think. So the Bianchi identities assume this simple form. If t equals 0, then you lose a whole bunch of extra nasty terms. Okay, so these are going to be important later. Now, I've kind of cheated a bit here because I've taken the derivative of R, supposedly using my connection nabla. So what I ought to tell you is that if you've got a connection on the tangent bundle, then for free you get connections on all of the tensor bundles as well. And I've used the connections on the tensor bundles to differentiate the curvature here. So note here that a connection on the tangent bundle Tx actually induces connections on, well, firstly on the cotangent bundle T star of x, and also on all tensor bundles big tensor to the k, lots of T of x tensored with big tensor to the L of T star of x. So you can tensor together as many copies as you like of the tangent bundle and as many copies as you like of the cotangent bundle. You get a connection on these vector bundles as well, which satisfying obvious product rule conditions. Let me give you an example of what I mean by that. So, for example, there is a unique connection nabla primed on T star of x. So, in general, if I've got a connection nabla on Tx, I'm also going to write nabla for all of the other connections on all the tensor bundles as well. But just for now, I'm going to write nabla prime for the connection on T star of x so we can distinguish it. So such that for all v and w in the sections of Tx and alpha in the sections of T star of x, we have, well, the lead derivative in direction v of alpha dotted with w. So this is just a function we get by contracting the one form alpha and the vector field w is equal to nabla primed of v of alpha dotted with w plus alpha dotted with nabla v of w. Okay, so here, this is a one form. We've differentiated in direction v to get another one form. We contract it with w, get a function. This is an equation in functions. On x. So this is just a kind of product rule. If you differentiate alpha times w, the answer should be what you get if you differentiate alpha times w and then plus alpha times the derivative of w in direction v. Now, if you used, there is a unique connection nabla primed which has the correct compatibility with nabla to make this true. If you choose a different connection nabla primed on this, this would be true plus some extra terms in kind of trilinear in v and alpha and w, but with no derivatives in. And in general, there are connections on all of these bundles such that whenever you take derivatives of sections of various bundles and then you use the natural contractions between tx and t star of x in all different ways you can imagine, what you get satisfies the product rules in a natural kind of way. Okay, I think we're supposed to stop at this point.